So I'll start from the beginning very quickly. This is a database about cars it's a repository with data about cars which were in fashion in the 60s or 70s in the United States with their characteristics. And well, we can load this dataset by using the command at line 79, which is simply data, that's a function which accesses data that are already inside the R package, basic package. The name of the dataset is empty cards, so I use the command data, in brackets, the argument, which is empty cards, and the dataset is loaded. And then I can explore the first 6 lines of these datasets by using the command head, which shows 6 lines, the first 6 lines. Dataset is indeed quite longer. Let me check about the variables and what they are. So I'll use question mark empty cards. So we can have information about this data set. Now I need to enlarge this pane here. So we see that there are 11 variables, and I'm looking at the variable VS, the number 8. So we see that there are 2 types of engine, V-shaped and striped. And the subject with V-shaped engine are labeled with 0, while the cars with straight engine are labeled with 1. So you see, this is a numeric variable indeed, but it's not a number. So 0 is not a number. It is just a code. And 1 is not a number. It's just the code for straight engines, right? So this is a categoric variable. And it has 2 classes. The class is 0 and the class 1, right? So what can I do to describe this data? The first thing, and maybe the only thing I can do and I can think of, is just to count the number of cards in each class, right? So what do? We use the function table, then the variable I want to tabulate, that is empty cards, that's the name of the dataset, dollar, extracting the variable VS. And here we go. So this is okay for counting subjects in nominal variables. So we see that there are 18 cars with a V-shaped engine and 14 cars with a straight engine, right? So these are the so-called frequencies. Absolute frequency. Absolute frequencies. That is the count of subjects. Right? So this is the first definition, absolute frequency. That is the absolute count of subjects in a class. for a categorical variable. And of course, the sum of counts must match the number of individuals. Right? Any question? Do you have any question? No. Okay. You? Right. Well, then we can calculate the relative frequency. Relative frequency is given by the count of subjects. I copy this comment here, dividing by the total number of subjects. So in order to find the total number of subjects, I use the function length. With a vector, length returns the number of subjects in the vector. And the vector is empty cards and so we are up above at the numerator, we are counting the subjects in each class, and then we are dividing by the total number of subjects, and we get the relative frequencies. So it's, you see, 56.3% in the first class, 0 class, and 43.75% in the 1 class. So this is an information. And we can't go much farther than this with categoric data. This is just important. This is the proportion of subjects in each class. If we multiply by 100, then it's the percentage. So it represents somewhat a probability. What is the probability of getting a car with a V-shaped engine? Well, we know that it's 56% approximately. If we take one car random, then we have 56% probability that it has a V-shaped engine. And you see that cars with V-shaped engines are more likely in this sample. So if we have, these are classes which have no intrinsic ordering, they are not ordered according to any criteria. So we could work with classes that have an intrinsic ordering, so ordinal classes. If we work with ordinal classes, so describing ordinal variables. There is one ordinal variable which I considered, that is gear. So empty cards and extract gear. You know that gear is the number of gears in that case. So we see it might be 4 when the engines have 4 gears, or 3. And then we have also 5. So some cars have 5 gears. So we have basically 3 classes, 3, 4, and 5. And we know that these classes are ordered because 3 is less than 4, 4 is less than 5, and 3 is less than 5. So we can calculate the absolute frequencies as we did before. Table, the variable changes, of course. Empty cards and extracting gear. So we see that there are 15 subjects with 3 gears, 12 subjects with 4 gears, and 5 subjects with 5 gears. And these are the absolute frequencies. Absolute frequencies. Then we can calculate the relative frequencies as we did before. So length, empty cards, and extracting here. So we see that 47% cards have 3 gears, which is the mode. So a new index of central tendency. So the mode is the class with the highest frequency. So in this case, the mode is 3 gears. That's meaningful. And another meaningful expression of central tendency, which we can give. So you see what central tendency means. Central tendency is not necessarily central. In this case, it's more towards the edge of the distribution, right? So there is something, so these are relative frequencies. Here we can go a little bit further ahead because we can calculate the cumulative frequencies. Cumulative frequencies are the frequencies for one class and all the previous classes. So let me use so these are the absolute frequencies we can accumulate by using the cum sum function. So I can accumulate, I use 2 nested functions here. You see? Cum sum, and inside the brackets, I put the table function. So I take the table of frequencies and make the cumulative sums. And you see what happens. The first class, the 3 years, is still 15. But the second class is no longer 12, it is 27, because we are summing 15 plus 12. So we are summing the frequency of the second class with the frequency of the first class, because it's the previous class. And of course, as we have 3 classes, the last class has frequency, cumulative frequency, which is equal to the total number of observations, because we are summing the frequency of the third class with the frequency of the second and with the frequency of the first. So it's the whole number of individuals. And we can also calculate cumulative relative frequencies. Now I'm doing this slightly different. I'm assigning here, these are the RF relative frequency. So I'm assigning the relative frequency to a variable that I will call RF. And then I will make the cumulative sums of this table here. Oops. Made a mistake. Oh, here we go. So these are cumulative frequencies. We can calculate cumulative frequencies only for ordinal variables. We cannot calculate for categoric variables, for nominal variables, because there is no intrinsic ordering. So I do not know what are the previous classes. right? So these are cumulative relative frequencies. And as you see, the last class has a cumulative frequency of 1, because the proportion of subjects in the third class and all the previous classes can only be 1, because all subjects are in the third or previous classes. So here we go. Let me check whether, so it looks as if the internet connection has come back. I'll keep on with my phone for a while until we pause, and then I'll change, I'll swap. Here we go. Yesterday we made some, well, we do this later. Let me see what else I can tell you. I can tell you about some possible descriptive stats for distribution of frequencies. I can have other variables. For example, here, this is not really only an ordinal variable. It is also a count variable, because it expresses a count. So because we have 3 classes, 3 gears, 4 gears, and 5 gears. But there is also a distance property, because we see that the distance from 3 to 4 is the same as the distance from 4 to 5, and the distance from 3 to 5 is twice as much the distance between 3 to 4. Okay, so there is also an intrinsic property of distances. So this would better be a count variable. So it's a discrete variable. Discrete variable. So this is more similar to a quantitative variable in some instances. So we can calculate the mean. So we could write mean empty cards and gear. Right? So this is possible. Of course, what we get is 3.7, which is a value which it is impossible to find in the sample. We cannot find a car with 3.7 gears, because either the gears are 3 or they are 4. Okay, but it makes sense. It makes sense to say that the mean for this population is something in between 2 classes. So it makes sense, even if it is a value we cannot really find. Okay. Well, it is perhaps useful to think about what happens when we have a quantitative variable and we discretize it. So I'll tell you something about this. Discretization. Let me take another data set, because that is what I need now. It is on the CO2 variable, which I can load. So this is another data set, right? And we'll explore it. So what does it contain? You see that it is a vector. All right, so let's explore this by asking R to give us further information. So, all right. So be careful because C and O are small letters, not capital letters. Because if you write them capital, you get another data set, which is not the one I want to use at the moment. So this, you see, these are atmospheric concentrations of CO2 expressed in parts per million and reported in the preliminary 1997 SIO manometric mole fraction scale. So we don't care about the measurement unit. This is a time series of 468 observations, monthly observations. And you see that this is a vector of observation where we explored the first 2, 4, 6 elements by using the head function. So the head functions works both with data frames and vectors. Yeah, we see 6 values. Unless we want to see more than 6, because I can write CO2 10, 10, then I see 10 values. So I can ask how many values I want to see. But the default value is 6. And perhaps you might be interested in knowing that we have the corresponding function tail, so head and tail. Ciao, Carlo. Head and tail CO2, and it shows the final 6 values. So these are all functions we can use to explore big data sets. So what can we do here? What can we do? We can, calculate the mean, because this is a quantitative variable, right? So mean CO2, and we get 337, roughly. But if we want to represent this vector, we might decide that we want to discretize it. I mean, making a table where the CO2 variable is divided into intervals and count the number of individuals in each interval. That is what I mean. And it is easier if we do this together and then we comment on what we obtain. So we do this and then we stop for 10 minutes. First thing, I need to know what is the maximum value. The maximum value is C max CO2. Putting it a bit upper. Then it is 366. So the maximum CO2 concentration is roughly 3 per 1,000. A little bit more. Then the minimum value is 313. And this is the variability range for the vector. Then I decide to break it in classes, and I define the classes. The classes are obtained by using the cut function. So please cut the variable into intervals. The variable is CO2, we have seen it, and then we have to provide the breaks. So the breaks are, let me write 310, 320. So I could make a sequence here, but I will not do that. 330, 340. So it is more transparent if I do like this. 350, 360. Then the final class, which is slightly above the maximum, is 370. So what are we telling to R? We are asking R to take the quantitative variable and break it into classes. The first class goes from 0 to 310. The second class goes from 310 to 320, and so on. So we have several classes, right? Now we get the classes. Look at the classes result. So you see that every subject has been assigned to an interval. Look at the intervals. For example, the first subject, which is up here, it is located in the interval from 310 to 320. And you see that the interval is left open and right closed. Look at the parentheses. Okay? So what does this mean? It means that if I have exactly 320, then it goes in this class because the interval is closed, right closed. So now we can use the table function to count the subject in the classes. And here we go. This is a distribution of frequencies. I hope it is clear. It means that we have 70 individuals within the interval from 310 and 320. Then we have 117 individuals in the second class, the interval from 320 and 330. Look here, 320 is left, the second interval is left open, meaning that 320 goes in the first class. Exactly 320, not in the second. So we must have a criterion. This is not absolutely right, but this is our criterion here. So what is the purpose of such discretization? The purpose is simple. We can describe in few classes a quantitative variable, and we can give the reader a better perspective on this variable. Because we could use the mean and the standard deviation, that's okay. We have a measure of central location and a measure of spread. But here, with this distribution of frequency, we give also an indication of the shape, because we see that the mode is the second class. We see that we have more individuals above the mode and less individuals below the mode. So we see that this is not a symmetric distribution in terms of shape. And we see this because we use a frequency distribution. And I could calculate the mean by using that frequency distribution. That would be a weighted mean, because I simply multiply the number of subjects by the center of each class. But we will not do this. It doesn't matter for us. But it's something to know, right? So a few more information. First, we can describe graphically frequencies, relative frequencies, going back here. Here we go, by using pi. Okay, so it makes simply a pi for relative frequencies. If I give absolute frequencies, then it draws the pi by determining the relative frequencies. Pi's are useful to describe relative frequencies, because the whole pi corresponds to 1. Of course, we can modify the colors and whatever in the pi, but we will not look at this now. It doesn't matter. This is just an introductory course. Then if you have to take more advanced courses in R if you want to learn those things. We are just introducing.